Okay, so thank you very much for the introduction, and thanks a lot to the organizers for this very nice conference and for inviting me to present my work here. So this is a very recent result that came out on the archive only last week, and this is the first time I talk about this. So please forgive me if something is not clear or could be stated better. And is it possible to remove this? Okay, good. So this is work in collaboration with an experimental group, the group of Mark Kasevich in Stanford. And this is the result of some joint discussions on what does it mean to measure a superposition of gravitational fields. And of course, this discussion was very much related to what they have in the lab. And what I'm going to talk about today is my take on this discussion. So, doesn't change the slide. Okay. Okay, thanks. Okay, so this is the plan of the talk. So I'm first going to introduce the topic. Then I'm going to very briefly review what we mean when we talk about gravitational-induced entanglement, for those of you who are not familiar with the discussion. Then I'm going to give a theorist description of their experiment, which is the gravitational Aharonov-Bohm experiment. Then I'm going to introduce quantum reference frames, but Czesław already did a very good job on that, so I will probably go a bit more quickly. And then I'm going to tell you about the results of the paper. So let me start. So understanding the nature of gravity fundamentally is one of the major open questions that we have in fundamental physics. And of course, there are many different perspectives that we can use to understand this problem, but the one that I would like to propose here is a space-time related perspective. So this means that if in our two theories, of our two pillars of modern physics, general relativity and quantum theory, space-time has an extremely different role, and this cannot be reconciled. So in particular, we know that in quantum theory, matter is quantum. So nature gives us a quantum stress energy tensor. On the other hand, in general relativity, space-time has a double role. So in particular, if we take Einstein's equations, then we have a classical stress energy tensor that gives rise to a classical metric. And on the one hand, matter tells space-time what it should be, but also space-time tells matter how to move. And if we put a quantum stress energy tensor there, then we do not know anymore how to solve Einstein's equations. So how do we reconcile these two? Is there anything more that we can say? So there is a regime in which we can say a little bit more, and this is the regime in which we have a particle in a quantum superposition of positions. And in this case, we can formally find a solution to Einstein's field equation by linearizing the metric. And there is a formalism to do that, but this formalism doesn't tell us anything about the properties of spacetime, because spacetime is a background, and we take gravity as a perturbation on this fixed background. So, but the good news is that there is a framework. So we can study in this framework what the properties of a non-classical spacetime would be. And the other good news is that we have experiments that are getting more and more precise and that will be able to test this situation in the future. So in particular, there are two different directions that experiments are trying to push. One is to measure the gravitational field that is sourced by lighter and lighter objects. So at the moment, the record is this paper on the top left corner. So it's 90 milligrams. And the group of Markus Aspelmayer in Vienna has measured the gravitational field that is sourced by a 90 milligram mass. On the other side, we want to put particles in a quantum superposition, increase the mass of these particles, and keep them in this state for longer and longer times. And there are different experiments that are trying to push the limits, or the experimental limits on that. And so this one here in the corner, maybe I will just point it here. This one here is a recent paper by Markus Aspelmayer, where he gives a very clear description of what the experimental challenges of realizing this type of experiments is. So if you're interested, just go and read this paper. But I would like to focus on a different, on more theoretical questions now. And this is related to the recent discussion on gravitational-induced entanglement. So which type of theoretical implications will these quantum experiments have for the nature of the gravitational field? And this is not a new question. This question has been around at least since 1957, when at the Chapel Hill Conference, Richard Feynman proposed a thought experiment that involved a mass in a quantum superposition, and concluded that if you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. And by gravitational quantization, he meant the state of the gravitational field can be in a quantum superposition. And there was a lot of debate after this paper. There were a lot of follow-ups and proposals to test the quantum state of the gravitational field. I do not have time to go through these results, so I will just move to 2017, when there were these two papers on the archive on the same day that proposed a protocol which involved two masses that become entangled via the gravitational interaction. What is this protocol? We have this blue and this red mass, and we initially prepare them in a product state, each of them in a quantum superposition of two positions. Then we let them interact via the Newtonian field between them. And after some time, if everything goes as with the Schrödinger equation, then we find that they will be in an entangled state. At this point, we can perform an experiment to test whether the state is entangled. So the argument that they were using there was a quantum information theorem, that is that local operations and classical communication cannot generate entanglement. Hence, if you assume that gravity is a mediator, is a physical degree of freedom of its own, then the conclusion of the papers was that gravity is not a classical channel, so it has quantum properties. Now, there was a lot of discussion about this result, because there are many subtleties in the interpretation of this result according to the conclusions of these papers. And, well, regarding the LOCC theorem, the application of the LOCC theorem itself to gravity, but also that maybe the Newton potential is just pure gauge, so it's not a dynamical degree of freedom, and hence this would imply that that this experiment is testing the quantumness of matter and not of gravity. On the other hand, other people, like on the other side, think that this could be explained with gravitons. But okay, these are all positions, but what I would like to emphasize is that there are a lot of interesting observations, like, for instance, how do I treat the gauge split when I have to talk about the superposition of gravitational fields, and the gauge split is not physical. I can take different gauges. I can change the reference frame, and hence the Newtonian potential is not anymore just a Newtonian potential, but if I go to an accelerated frame, I have emission of radiation. locality of interactions. There are, beyond quantum theory, I could have alternative explanations of these effects. So there are a lot of, so I don't want to go into these arguments, but I just want to say that there is a very rich perspective and a lot of interesting observations that can be made and can contribute to the discussion. So this is what I wanted to tell you. So it was very brief review. Now let me go to the experiment that was done this year. So this is very recent, published very recently, 2022, in Mark Kasevich group in Stanford. So this is, first of all, atom interferometry. So you have to imagine that there is this big cylinder that is like 10 meters high, and on the bottom there is a source of the particles. So I'm not an experiment, so I'm not an expert of this, but and they shoot these particles up, and then they split them. So they give them a different kick, and according to the kick that is given in a quantum superposition, they will reach a different height. You see the red particle, for instance, it reaches a different height in the gravitational field. And the two red particles, this is just one red particle in a quantum superposition. And then it goes down again, and then you recombine the superposition. So the blue particle is something that is necessary for the experiment because it's a reference, but we are not going to talk about it in the following because from the theory point of view, it is not relevant to our discussion. But in addition to these particles that are in free, so this scheme here is in a freely falling frame, is drawn in a freely falling frame. And in addition, they had this half donut that you see here is actually a tungsten mass. So it's a piece of tungsten that weighs 1 kilo, and this will be the relevant source of the gravitational field that they considered in the experiment. So what happens is that according to the path that this red particle follows, there will be a different gravitational pull. And this experiment is sensitive to a regime of the gravitational field that is beyond the linear regime. So it's really the 1/r potential, basically. And and the distance between these two is 25 centimeters. So now we can simplify this experimental scheme in the following way. So basically, what we will consider, so the Earth factors out, that's the first thing, because in the experimental data, you don't have the sensitivity to see the difference in the gravitational field of the Earth, whether you are up or down. And so you can just consider the source and this A particle. And then the goal is to measure the relative phase at the end of the interferometer. And this relative phase is really the difference between the potential. So it's the interaction, basically, between the particle and the gravitational field sourced by the tungsten particle. OK, so given that, now, what is our question? So the question is, let us take everything that we know from this experiment and from similar experiments. Let's put all the ingredients together, and let's see what we can rely on. Then, which additional assumptions should we add on top of what we already know in order to see a superposition of gravitational fields? So this is not a superposition of gravitational fields, as it is. We need additional elements. Which are these elements? And why is this interesting? To me, this is interesting because if there is such a theory that has a superposition of gravitational fields, then this will likely have to obey these principles that we identify here. So this is why I think this is relevant. And also, I think it's interesting because knowing what we are missing will help us to identify which observations, which experiments we need to build in the future in order to see this, in order to have for everybody to agree that this will be a measure of the superposition of gravitational fields. So what do we know? So we know that classical gravity holds for particles that are as light as 90 milligrams. That was measured, and we can take it. Then we know that the equivalence principle is also valid up to 10 to the minus 12 parts. And this was also tested. Then we know that there are gravitational waves. This has also been measured. And here I'm just talking about all the classical things that we have measured for classical gravity. And then we know that these experiments measure the gravitational phase shift between the different parts of the interferometer. And we also know that if I take a classical source of gravity, such as the tungsten mass, and I want to put quantum theory of the atom of the particle in the interferometer on top of that, these theories are compatible, so I can write a Schrödinger equation and the particle obeys the Schrödinger equation. And notice that here I want to emphasize that it's the beyond the linear regime, it will be relevant here in the following to relate this to gravitational induced entanglement, because this is the regime that we need in order to have entanglement, the gravitational induced entanglement. The linear regime would not be enough because you will not have generation of entanglement if you are in the linear regime. Okay, so what else do we need to add on top of this? And we identified 3 principles. And I will just read them and then comment on each of them. So the first one is the existence of gravitational fields. What do we mean? Any massive particle that is well localized at a position x0 sources a gravitational field G with functional form G of x minus x0. So the important words here are any and well localized. Any means that any particle, so it doesn't matter the mass, any particle sources a gravitational field, whatever the mass. And well-localized is important because we're not saying anything about a particle that is in a quantum superposition of positions. Then, field energy principle, the phase of an interferometer is a function of the energies of the fields that interact with the interfering particle. And the third one is the quantum relativity principle that is very much related to what Časlav called the generalization of the principle of covariance. The laws of physics take the same form in every reference frame, including the reference frames associated with quantum particles, hence quantum reference frames. So I will just comment now on these 2, but first I was planning to give an introduction of quantum reference frames, but maybe I can cut it short, since Časlav already did a very good job. So the idea of quantum reference frames is that reference frames are physical systems, and physical systems are ultimately quantum. So basically, we want to take, if we take these 3 G's, and we have A, B, and C, and we take the perspective of C, then we associate to vectors that are that correspond to the relative distance between C and A and B and A, and then if we go to A, then we want to associate a vector that corresponds to the relative distance between A and C and A and B. And this is what happens in classical reference frames. But in quantum reference frames, we want to put the rocks in a quantum superposition and make sense of what it means to attach a reference frame to one of these rocks that is in a quantum superposition state. And the picture is very similar to what Časlav showed already. And so basically, here we want to take a transformation from a reference frame that is centered in C to one that is centered in the position of A. And we do that by a quantum superposition of translations, for instance. And I'm going quickly here because Časlav already explained this in a lot of detail. But what I would like to stress, so first, is that this transformation is invertible, and then that a result of this quantum reference frames formalism is that entanglement and superposition depend on the quantum reference frame. So this is an important property for what follows, and the other one is that a general quantum reference frame transformation can be understood as a superposition of classical transformations. So what we can write is something like that. And so far, we have roughly this structure for all of them, where the first part here is just a standard reference frame transformation. And the alpha I would normally be a parameter. But this parameter in quantum reference frames is promoted to an operator that is controlled on the state of the quantum reference frame. So this is just a general structure. So now, how do we describe this experiment with quantum reference frames? So on the left-hand side, I have this simplified description of the experiment of the gravitational Aharonov-Bohm. And on the right-hand side, we have the description from a quantum reference frame that is centered on particle A. So in this case, we will have a superposition of positions for the source mass. So basically, the tungsten will be in a quantum superposition. And what I want to say is that this description tests a superposition of gravitational fields only if these three assumptions that I mentioned before are valid. So we need to have these three assumptions to have the equivalence between these two situations. Why? Okay, to understand that, let's see what the field energy principle is telling us. So usually, we write the phase shift of an atom interferometer as an interaction potential between the mass and the gravitational potential. However, it is equivalent to write it in terms of the gravitational energy that has that form. And if we do that, basically, we can write the phase shift in terms of the difference between the energy configurations of the gravitational field alone. So in quantum theory, this would be something that you obtain by acting on the state of the gravitational field. So if you want, you can, so this assumption is formulated in a different way, but it is similar to what we say when in the gravitational-induced entanglement experiment, we say that the gravitational field is not only a potential, but it is a dynamical degree of freedom, and that it is related to gravity being a mediator of the interaction. So, but we formulate in terms of the gravitational field being able to carry energy because we have an indication from gravitational waves that this is true for the classical gravitational field. Then, what about the quantum relativity principle? Again, we can understand this by resorting to our standard description of physics. And in particular, let us just consider linearized gravity, where we have a differential equation for the metric perturbation, and this will be equal to the stress energy tensor. And then we can formally write a solution of a particular solution of this differential equation with the Green function. And now we are going to take two arbitrary masses. So we are not making any assumption of what the mass of the particle 1 and particle 2 is. And just consider their stress energy tensor. And we know that in linearized gravity, we can just take the sum of these two stress energy tensors, and the principle of linear superposition holds. So, and we can plug both of them into this, thanks to our principle 1 that says that any localized particle is sourcing a gravitational field. So, if then we can recast this term so this would be the coupling between gravity and matter, and then we just plug this expression and this expression inside, and we can recast this as T1, the Green function, and T2. So you see, this is an expression that is fully symmetric, and in particular, if you look at T1 G, this can give H1, and T2 G, this gives H2. So the gravitational field sourced by either mass 1 interacting with mass 2, or the gravitational field sourced by mass 2 interacting with mass 1. And so this tells us that it is equivalent in classical physics to use either particle 1 as a probe and particle 2 as the source, or particle 1 as the source and particle 2 as a probe. And so I'm not saying anything special here. This is just a simple result that you can derive. But what the quantum relativity principle tells you is that this also holds when you have a quantum superposition of probe or source. So if I have a situation where I have the source in a classical state and the probe in a quantum state, then it is equivalent to have the probe in a classical state and the source in a quantum state, but with the detectors on the source. So the detectors are really the core of this quantum relativity principle, and then I can take a quantum reference frame transformation to the particle, to the source particle, and then I will have an equivalent situation to what I have here on the left-hand side, but with the source in a quantum superposition. So this is a statement. And how does this compare with gravitational-induced entanglement? So do we actually need gravitational-induced entanglement? This slide for me is just a motivation to think about what we really need in order to measure superposition of gravitational fields. And here I just want to make a simple observation that is, so let us consider, this is the BMV setup, so the gravitational-induced entanglement, that the two masses that are prepared in a quantum superposition and that have that interact by the gravitational field. Now, this is particle B in position A, and this is particle B in position B. And after some time, we will have a state. So here I just grouped the state in a convenient way, where particle A is in a superposition of A, C, and D, and I have a phase. And the same holds when the particle B is in this position. And now let us focus on what is in these brackets. So this is a gravitational Aharonov-Bohm experiment when the particle is in position, so basically this would be the tungsten in position A, and this would be a gravitational Aharonov-Bohm experiment when the tungsten is in a position B. And I say that this is a gravitational Aharonov-Bohm experiment because the regime in which we need to be for these phases to be the phases that you get in the gravitational-induced entanglement experiment are the one beyond the linear regime. So this is exactly the regime that this experiment is testing, but for a classical position of the tungsten. So this is basically everything I wanted to tell you. And so for me, the motivation of this work is that realizing gravitational-induced entanglement in the lab is hard. And so it would be great if we could come up with other tests that we can realize before that have an equivalent physical content. And I think that the study of the fundamental principles that underlie this description and identifying which other assumptions we need to give up in order to demonstrate this experimentally can be helpful because it can give us both a clearer picture of what the fundamental physics underlying this experiment is, and a roadmap to develop new experiments which can give up at least some of the assumptions that we still have based on the current experiments. And I would like to thank my collaborators and also all of you for your attention.
So we have time for questions from the audience or from the online. There is none? Okay.
Sorry, just to see if I understand correctly. Are you saying that this experiment of the tungsten mass plus some extra assumptions imply an argument in favor of the quantization of the gravitational field?
If you add additional assumptions.
Okay. And which are they? Can you explain them again?
This. So the fact that every massive particle that is localized sources a gravitational field, that you can interpret the phase of the interferometer as a function of the energies of the fields that interact with the particle. So this means giving a dynamical degree of freedom to the gravitational field, and the fact that the laws of physics hold in every quantum reference frame that can be localized.
Okay. So for you,
but
this
quantization,
experiment...
quantization, you have to contextualize what I mean by quantization, like gravitational field in a quantum superposition.
Yeah, semi-classical somehow, or...
Well, the fact that the state of the gravitational field is in a quantum superposition.
Yes.
Yeah, I'm not talking about gravitons.
Yeah, sure, yes. And this is for this experiment, like the cow experiment, for example, would not give you the same argument.
So the cow experiment, for instance, is linear, is the linear shift. So you will not. It is not equivalent to the gravitational induced entanglement.
Okay.
That's one of the arguments. Yeah.
Okay. Thanks.
Thanks. I guess I have a follow-up question. So if I understand the number 3 to be applied to any physics, why do I need 1 and 2?
Because you could still have a description of gravity as a background potential without a dynamical degree of freedom, for instance. And this would still be compatible with the experimental results. And so you would not be able to detect. So to conclude that the gravitational field is in a quantum superposition state.
Thanks.
Okay, so if there are no questions online from what I saw before. So if there are no more questions, I think we can thank Flaminia again and all the speakers of today's session.